There we go. Okay. Good morning. Sorry. I'm just having that kind of a day. I'm not on mute. I'm sharing my screen. That's pretty good. And I started recording. Just thinking. Okay. For review, we started inverses last day. Inverses are basically when we kind of solve for y instead of x, right? And so we had this cute little example of a designer, clearly an American designer, going to Europe where they use Celsius instead of Fahrenheit. And so we use the conversion formula to move back and forth between Celsius and Fahrenheit and vice versa. So this is a linear function, right? Because there's just one input, right? If we're trying to solve for the Celsius, then we can put in the Fahrenheit and solve for the Celsius. So we have one input and we rearranged it to solve for F. So we can put in any Celsius and solve for the degrees Fahrenheit. I just realized I just jumped right in. Are there any questions before we start? I already started, I know. Emily, that felt fake. I know, it kind of was. I'm just so pumped about inverses. So here we go. So what we said was, okay, one of the rules for having an inverse, so only some functions have an inverse. In order to have an inverse, they have to be one-to-one. Okay, and I think that's on the next page, maybe. Blah, blah, blah. Let's do this. In order for f of x to have an inverse, which we denote by f to the -1 of x. Now this is not a power, and oh yeah, that's why we stopped last day, because I had left this space clearly meant for something, and then I really couldn't figure out what I was supposed to say here, but now I remember, / I looked it up. This -1, right, that's not a power, right? Context will tell us that if it's on the f, right, then it means f to the -1, which is the inverse of f. Okay? And so this is not a power, although what does taking something to the -1 do? Puts it, it's not 1 over f of x, but kind of, right? So that's why we use the notation, but I'm gonna scratch that, right? Not a power. Context tells us, oops, is the inverse of f of x. Okay. So when it's on, I thought I was highlighting. When it's on the f, right, then it means that it's the inverse. So continuing this thought, in order for f of x to have an inverse, the inverse of f of x must be 1-to-1. And that's when we traced back to the very, very first section 1.1, and we said, okay, what does it mean to have a 1-to-1 function? Well, first it has to be a function, right? So it has to pass the vertical line test. Then, in order for it to be 1-to-1, it has to pass the horizontal line test as well. Meaning it can only pass at one time. right, as you draw horizontal lines. So it has to be a function, of course, and then we have a special case of functions which are one-to-one. And so we're going to look at, okay, how do we know if it's one-to-one? Maybe if we don't have the graph, right? That might be harder, but we're not there yet. There was one other thing. Note. See, there was a lot I wanted to smush in here, I guess. The inverse of f of x is not the same as f of x to the -1, right? And so that's going to be really important because this, right, f of x to the -1 is 1 over f of x. You know? So they're different. Again, not a power. We could. I think I saw one on the assignment.
Oh yeah.
Where it asks you to find the inverse and then find just 1 over f of x, which would be different. How about a little example? If f of 3 is 2, so if I input 3 and I output 2, then what do we know about the inverse? Well, we know that if I input 2, it's going to output 3, right? Because it moves in the opposite direction. So then we know that f inverse of 2 must be equal to 3, right? Output becomes the input, and the input becomes the output. Which means that we have this kind of jumping back and forth situation, right? And so we have the domain of f. Remember, the domain is all possible values that I can put into f, right? So I can't take the square root of a negative number and I can't divide by 0, right? That's all from last day, well, and a couple of days now. We're gonna need to have a good handle on those. So we've got the domain of f, so all the possible inputs that I can put into f. Okay. And then I have all the possible outputs of f over here, the range of f. Okay. So now, if I'm moving in the regular function f of x, then I have an input a and I get an output b. But now, if I'm using the inverse, right, the range of f becomes the domain of the inverse, right? And the domain of f becomes the range of the inverse. Okay. So here, I'll highlight the range of f is the domain of the inverse. And the domain of f is the range of the inverse. Oh boy, now I've done it again. Can't remember what I was going to put here. I do, but it's not going to take this much space. Oh well. Basically going to write it out again. It's important. Let's do it. So the domain of f of x is going to become the range of the inverse. And the range of f of x becomes the domain of the inverse. There. I didn't need that much space, but that's what I wanted to say. So if you know the domain and the range, Now we focused on the domain because the range kind of just falls out from the domain, right? So we haven't talked about the range so much, but we'll see some examples. And so if I know the domain and range of the original function, then I know the domain and range of the inverse function as well, because they'll just be swapped. Okay. Function compositions back to haunt us. So the original function and the inverse function undo each other, right? And so if you have f of a is equal to b and the inverse of f of b is equal to a, right, that's the definition of the inverse, okay, then it should bring us back to the original input. Okay? So if you compose these functions together, you should get the original input as your answer. So one way to check that you have the right inverse function, right? One way to check that the f inverse of x you found is in fact the inverse is by taking f inverse of f of a, and does it equal a? Right, you should get back to just the input. This is a function composition, right? So you stuff the original function into the inverse function as the input, and then you should get a. Or similarly, so usually I do both. F of f inverse of a, we should check that it equals a. Or x, or whatever you want to use as your input. So we'll use that. And this is one of the ways that I'm going to test your function compositions, right? Is I ask you to find the inverse on the test. And so then you solve for the inverse function, which we haven't really done yet, but we will. And then a follow-up question is going to be, okay, now use function compositions to show that this is in fact the inverse, okay? And so then we're gonna do this. I'll even write it down. This is one way I will test function compositions. You're so happy about that? Smiley face. Okay. We already talked about one-to-one functions. Okay, so in order for a function to have an inverse, we said, okay, it has to be a one-to-one function. Okay, and so what does that look like? I have a graph like this. Let's start with a nice, easy, just a linear function. Right? It has to be a function. Right? And so the vertical line test says it's a function. And then the horizontal line test, HLT, says it's one-to-one. Right? So if you have a graph, or if you know what the graph looks like, right, that's why it's so useful to have those toolkit functions kind of in your in your mind, what do they look like, right? And so if we just have a peek at, where are those little guys? They're all functions because they're toolkit functions. So we don't need to do the vertical line test again, but let's do the horizontal line test. Well, this one's pretty boring, and it's not one-to-one, right? Because I need to be able to put in some unique input and get a unique output, right? Which I can't in this case. Constant functions are pretty boring. Linear functions, they're one-to-one, right? Because I can put in some input, any input, and get a unique output. Right? How about the absolute value function? If I put in 2 or -2, the output is 2 both times, which is going to be, if you're trying to work backwards, that's where you run into trouble, right? And so now this is not a one-to-one function. What we do, if we have to find the inverse, then we restrict the domain to some area where it is one-to-one. We can split them up. Okay? So that's what we'll see. But so we will be able to find inverses on restricted domains still. Not one-to-one again. Same scenario, right? I put in 2 and I get 4, and I put in -2 and I get 4. Well, now if I'm using the inverse and I put in 4, then it's not going to know which way. Does it go to 2 or -2? It can go to both. And so now it's not one-to-one. But if we restrict the domain, let's say from 0 to infinity, right, then all of a sudden I have this one-to-one function that I can work with. Okay? One-to-one. There's a ever so slight curve. It just keeps curving, so it's never flat. So it's one-to-one. It's one-to-one. 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 Not one-to-one. Right? Just using that horizontal line test. So knowing what these animals look like is going to be useful. Okay. Yeah, I feel like they might have just been in 1.1, but I posted them. Oh, good, actually, because it kind of depended on today, how far we get today, but I did pick a test day, which might be nice to know. I realized. Where did I? Oh, here. So under the textbook and other resources, I have just the graphs of the toolkit functions, which might be nice. Okay. So like I said, it kind of depends on, I've committed to a test date, but the material on it depends on how far we get, obviously. So we'll see how far we get into 2.1. Oh, this is so important. Oh, here we go. And so next week, we're going to work through more of chapter 2. And then we'll have to do absolute value functions. And then I've got us moving into chapter 3. It's kind of a buffer. I'm not going to test chapter 3. The test 1 will only be on chapters 1 and 2. And so we'll see if we kind of start chapter 3 or not. But I've also got the test 1 review on probably the 10th. And then you've got your test 1 on October 15th. And it's just on chapters 1 and 2.
The whole class?
Yeah. So, let's see here. How about I write that at the top here because I totally forgot. I'll do it in all caps. Test number 1 is on October 15th. That's good to know. Now, a question for you guys is, does that conflict with any of your other tests?
After my birthday.
Hey, what a way to celebrate. So here's the thing. If you guys ever feel like, I wish Emily could change this, I can. You just need to tell me. Okay, so if you come to me as a group and you say, hey, can we have the test on the Thursday, as long as everyone agrees, I'm happy to make changes. Okay, and so I'm totally flexible. We don't have any Friday classes, but Fridays before a long weekend, usually I'm like, do you guys just want to watch a video? And then, so we can just get jiggy with it. So if you come together as a group and you tell me what you want, more than happy to do that. Okay, but for my planning reasons, test number 1 is on October 15th. If it turns out that you have many tests on that day already, then that's bad, and I can be flexible. Okay, I don't like to bump it forward because that's rude. I would bump it to probably the Thursday or something. Okay? And so, but let's plan on that. Usually they have your test dates to you guys, but maybe not yet.
Some of them, and they say that, oh yeah.
Oh, maybe it's because I have 2 tests, and if they're only doing 1, then the timing would be different, right? Because we'll do 1 in October, 1 mid-November, and then the final exam. Kind of is how it's going to go. But the tests are not cumulative, right? So test 1 will be chapters 1 and 2. Test 2 will be chapters 3 and 4, kind of siloed. And then the final will include some of chapter 5 and a little bit of 6. Okay, good. Can't believe I forgot that, but I mean, class isn't over, so I guess I sort of remembered in a way. Oh, and on Mom, so for those assignments, I have been seeing some forum posts, which is very cool. I don't get notifications about those, so it's just if I log into Mom, then I see them. And so sorry if I missed them, but then I've been hopping in and say, oh, okay, you got it. So that's cool. But so if you've asked me a question on there about an assignment question, and it's posted in the forum, I don't know what it looks like on your end. Maybe just send me a text and be like, hey, I sent you a question on Mom. Because I probably won't log in on the weekend. Okay, good. How about an example? We're going to start from the bottom. Now we're here. F of x is 1 to 1. We're told that it's 1 to 1. And has domain x greater than 2, not including 2, and range y less than 1, not including 1. Okay. Now we're asked to find the domain and range of the inverse. Right? And so, okay, f of x goes from x greater than 2 and maps to y less than 1. So now, if you want to, you could do something like this, where it goes from x greater than 2 and maps to y less than 1, right? So f of x goes this way, but the inverse goes the other way, and we're told that it's 1 to 1, which means that, okay, the domain then is that y must be less than 1, And then the range of the inverse must be that x is greater than 2. So you just flip them. So the domain of f inverse of x is y is less than 1. I'm going to change this y to be an x, right? Because I could use f inverse of y, right? But I have x as the input, and so I'm going to change this, but I'll use red to show that I did. To match the input. And then the range of f inverse of x is x greater than 2, but the function is usually mapping to y's just generically. And so I'm going to change this to be a y instead. To match the input. To it does look like nature. Oh boy. So you're just going to flip the input and the output. But usually when we say the input, we use x, and when we say the output, we use y, just generically. Okay. As we've done in the past, we can look at functions in a couple of different ways, right? We can use tables to represent functions. We can use graphs to represent functions, or we can use actual mathematical functions, right, which we're building up to. But we'll start with a table for a function. So here's our input, here's our output of f of x. Now, if we want to evaluate the inverse at 3, right? Okay. The inverse is going to yield the input from f of x that generates the output of 3. Right? And so let's map it like this. So I have the output of f of x is from an input of 1 to get to 3. Yeah. So how I would read this is that this would be f inverse of x if x is down here. Or if you prefer, using different variables, you can, right? F of x is y, but y is now the input of the inverse function. So now if you have to evaluate the inverse at 3, 3 is the input, the output is 1. And maybe I'll use a different color here, just because I'll do them on the same graph. And I'll use green here. So just moving backwards. What if you have to solve for the input of the inverse that yields an output of 3? So now you have an output from the inverse that's equal to 3. the input that makes that happen is 7. X must be 7. You can use X or Y. I just find sometimes it can be confusing because we use X for both, but do you guys want X or Y? Let's change it. There. As long as you keep them straight. This X is different from this X, right? That's the hiccup, but as long as you can keep them straight, you're good. Okay. I think I'm gonna bump this up here. So I want this bigger. So that's working with inverses given a table of functions, or a function as a table, I should say. Now, what if we have it as a graph? First, is this a function? Yes, it's a graph of a function because it passes the vertical line test. But now, is it one-to-one? Yes, it is. All right. And so it is one-to-one because it passes the horizontal line test, right? I only cross this graph once with each horizontal line that I can draw. Gonna do the same thing. Now with the graph, it's rough approximations. You don't have to, I don't expect you to be able to read it, you know, what is it at 3 here? I don't know, 2.5-ish, right? So f of x moves from an input here to an output here. Right? The inverse is going to take an input from the y-axis and give you an output on the x-axis. Right? And so now the inverse wants an input of 3. And so here, I'll just circle it like this. And so from here, we give it an input of 3, and we find the output must be 1. So it's working backwards. When you want to find the input, now the input of the inverse, right, is on the y-axis. And so we want to find the input that generates an output of 4. And so what we're going to do here, I'll use green, is, okay, I need it to map to 4. And to map to 4, I need an input of 2. So then x must be 2. Okay. Oh, and then I have scrunched it so it didn't span a bunch of pages. Any questions about those so far? Before we move on to the actual mathematical functions. Okay, so I've got add 2 pages for work roughly, and then add another 2 pages. I'm just gonna put it on its own page here. it's gonna be kind of long because what I wanna do is make that part A, and then part B is going to be confirm that it's the inverse using function composition, right? It's also a nice way to be able to check your work, right? Okay, how are we going to find the inverse? So to find the inverse, first thing I do is I replace the f of x with a y, so I don't have to deal with the f of x. Replace f of x with y. If you're comfortable just moving the f of x around, then that's cool, but I'm not. So what does that look like? Means y is 3x minus 5. Now the inverse, right? We already saw this with the Fahrenheit and Celsius conversion, right? I want to rearrange this so that now I give it an input of y to get the output of x that I want, right? And so really what I'm doing here is I'm going to solve for y, or sorry, solve for x. Haha, nice try. So if I start with y equals 3x minus 5, to solve for x, I try to get it on its own, but first I need to add 5 to both sides. Y plus 5 is 3x. And then to get x on its own, I have to divide by 3 on both sides. Y plus 5 divided by 3 is equal to x. Now remember, usually I would have written it as x equals y plus 5 over 3 immediately, but I wrote out this step just because it's been a while since we did algebra together. Because usually what I want to have is I want to have whatever I'm solving for on the left and everything else on the right. Okay, so now I can give it some y and it'll generate some value x, which is what I want. This is the inverse function, okay? But usually we change the notation a little bit. Oops, I think I've just been, numbering. We can rewrite the function by swapping x and y. So what does that look like? X is y plus 5 over 3 becomes y is x plus 5 over 3. The reason we do that is because we usually write f inverse of x, right? It should be f inverse of y equals x, right? Which is what we have here, right? I input some y and it returns x, but that's not usually how we write it. And so then the fourth step is replace y with f inverse of x. And because I am running out of space here, f inverse of x is x plus 5 divided by 3. I'm gonna add another page here. that's fair enough. Right, rearrange the function. There's a couple of I find that this up to this point is usually fine. And then kind of the motion of switching the variables and then rewriting it as f inverse of x, that's a little tricky in the beginning, right? But benefit of doing that is for when you have to answer part B. Part B is going to be something like use function composition I'll make it plural to confirm the inverse you found is in fact the inverse. If the function you found is in fact the inverse, then you should be able to take f of f inverse of x and it should yield x, and f inverse of f of x should yield x. So in our case, all right, we have f of x was, I'm gonna have to scroll back up here, 3x minus 5. And we found f inverse of x. And that's the reason we want to switch these so we don't have competing variables, is x plus 5 over 3. Use one as the input of the other. Now on the test, I'll only expect you to do one. We're going to do both, right? Which is why I made it optionally plural. We're going to do both, right? But you just have to show one. Technically, you should show both, but it's a lot of work. So let's do f of f inverse of x. Does it equal x here? And then here, I'll do f inverse of f of x equals x. Does it equal x? And then I'll kind of keep them separate, but I'll do them side by side, one at a time. Can you imagine? Okay. What does this look like? I want to use the inverse of x as the input into f. Right? So wherever you see an x, you're going to replace it with x plus 5 over 3, treating it as one thing. So we get 3 times x plus 5 divided by 3. Let me clean this up here. Minus 5. What's nice is we're going to see that these guys cancel, right? 3 over 3 is going to cancel. And so then I'm left with x plus 5 minus 5. But as far as I can see, that does equal x, which is great. Yee. Which means that the inverse that we found is, in fact, the inverse of the f of x that we were looking for, right? If you're not able to cancel things out and get to x, something's gone wrong. Okay? We'll do the same thing, but with the reverse stuff, reverse stuffing. So now, wherever I see, oops, oh, geez. Wherever I see an x here, I'm going to use f of x as my input, right? And so I have 3x minus 5. 3x minus 5 is going to be treated as one thing plus 5 divided by 3. 3x minus 5, there's brackets around there just for me to see that they're one thing, but they're not doing anything. So 3x minus 5 plus 5 puts me at 3x divided by 3. Party time. 3 over 3 goes to 1, and I'm left with x. It's a good feeling when you get to that x. Pretty fun, right? Something like that. I'll draw. So then I'll write a finishing blurb like, since f of f inverse of x is equal to x, which is also equal to f inverse of f of x, right? They're all equal to, or both equal to x, right? The inverse that we found is in fact the inverse. Hey. Okay. You'll see something like that on the test for sure. So it's a nice mashup, compositions and inverses. Okay. We'll move this up here. Hey. This projector does not want to do this today. Keeps turning off. Okay. First, let's do a little bit of the transformations from last day, which I didn't bring up because we're doing inverses today. But from last day, right? X minus 3 squared, if you had to visualize it, what would it look like? Nice. Also, if you have, yes, I wasn't clear though. If you start with x squared is your original function, then if it's x minus 3, it does the opposite of what I want to do. So I want to move to the left, but it actually moves to the right to compensate. And so you start here, this is your x squared function, and it's going to be moved to the right and maybe look something like this at 3. We'll confirm by mapping it in or graphing it in Desmos, right? But this is what we need to be able to visualize without Desmos, right? It's nice to confirm, but with a nice itty bitty function like this, recognizing what the root function is, right? X squared, and then the manipulations that have been made to it, right? Move to the right by 3 units. That's going to help us visualize the domain, right? But let's use Desmos to see. X minus 3 squared. So we did good. And I never did look into exporting, but on a roll. Hey. Cancel crop top. Because I don't want to have all of that there. So we need to be able to figure out what the graph looks like without the graphing tool. Right? I'm not going to go crazy, right? It'll be something like x squared, right? That's been manipulated a tiny, tiny bit. If we have to find the domain, well, let's talk about first the overall domain of x minus 3 squared. The overall domain, I can put in any value of x and there are no forbidden values of x, right? There's no division here, so I can't divide by 0, so that's safe. There's no root here. There's a square, but there's no root, right? And so I'm not restricted to non-negative numbers or anything. There's no restrictions on the domain. So the original, the domain, I'll say the overall domain of f of x equal to x minus 3 squared is, now I can't remember if I've introduced the set of real numbers. And maybe neither can you. Feel like if I can't remember, you're not expected to remember. But here I introduce it. It's like a fancy capital R. Now the set of real numbers you do a double back.
Yeah, it just looks like that. Do a little capture, so
Little flare. So capital R with a double back is the set of real numbers, which is any number from negative infinity to positive infinity. I feel like we did touch on it, but it's been a while. Right? So one way that we can say the set of real numbers, right, is from negative infinity to positive infinity. There's no restrictions on what x I can put in here. It's going to take a long time to get out to x equals infinity or negative infinity, but it does go there, right? So now we can use the vertical line test and confirm, okay, it is a function, but then we go to the horizontal line test and we see that it's not a function. You know? So what we're asked to do is, well, first, I'll do this. I'll just do a couple of lines here. Not one-to-one, since it does not pass the horizontal line test, HLT. Oh. Copy this. I'll erase this. Crop this up a little bit more because I just want the graph now. So if you had to restrict the domain so that it is one-to-one, there's actually lots of options, right? Bless you. I think my go-to move is just restricting it to these values of x, right? Any x greater than or equal to 3. Technically, what else is true, right? So if I just ignore ignore all this now, then it's one-to-one on this restricted domain, right? And so here, the restricted domain in this case can be, it can include 3 and go up to infinity. Round bracket on infinity. That's my go-to. Kind of going all the way to infinity. Like I said, what else is technically true? Oops. Oh, hey. Trying to erase those. Okay. Another option might be something like, well, I mean, you can just go to 5, right? That's kind of weird. We don't do that typically, but technically it's true, so I can't argue with that. But the other way would be to go from negative infinity up to and including 3 if you want. So an alternative restricted domain might be from negative infinity up to 3. Can include 3. Let's see if I can just copy this one. Right, you could go from 3 to 5. Technically, 3 to 5 inclusive is a restricted domain where it is one-to-one, but it's not one that we would use, right? Usually we let it go to infinity and we want to consider all the options, right? Is a restricted domain where the function is one-to-one, but this is not what we typically use. We usually, I tend to stick to the positive values, right? So we usually start at some starting point and then take it to positive infinity. So we usually start at the first point, trying to communicate what this would be in general. Kind of the first point where it could be one-to-one. Then extend to infinity. And by the first point where it could be one-to-one, in this case, would be at x equals 3. Right. Anytime before then, it wouldn't be one-to-one. So our restricted domain is on the interval, I'll include 3, it's up to you. Might be easier to include 3. 3 to infinity. So now, oops. We're going to include this here and only look at these guys, and these guys have gone away. So kind of going through some options here. But usually you would just skip to, okay, well, I know what this thing looks like here, and I'm going to restrict it from 3 to infinity, right? Or negative infinity to 3. But like I said, I like to deal with the positive ones. And so find a domain on which this function is 1-to-1, done, and find an inverse on that restricted domain. Okay. So now we're going to find the inverse of f of x equal to x minus 3 squared on the restricted domain. To find the inverse, right, what did we do first? I'll outline the steps again. I like to replace f of x with y, right? That's the nicest first step. So replace f of x with y. So then I get y is x minus 3 squared. Now, my second step is going to be to solve for x. So if I start with y equals x minus 3 squared, I'm trying to get x on its own, then I'm going to take the square root of both sides. Oops, so that means I get plus minus y, a root of y is x minus 3. Okay. X, we restricted the domain so that x has to be from 3 to infinity. So it has to be a positive, right? And so recall that the domain is from 3 to infinity. What does that mean? 3 minus 3 is the lowest I can be, right, at 0. And then if I go up 1, 4 minus 3, then I'm at a positive, a positive, a positive. So what does that mean in terms of this plus minus, which is technically true, but we've restricted the domain to only consider the positive versions of the square root, right? And so that's why we restricted that domain. Okay. So I'm going to do that in pink because that's on the restricted domain. The root of y can only ever be positive. So we remove the negative option from our answer. So now the root of y is x minus 3. We're still trying to solve for x, but we've kind of narrowed it down a little bit, right? We don't have to deal with the plus minus root y anymore. And so now I have the root of y plus 3 equals x, or rather, x is the root of y plus 3. And then, so now we do the sneaky step where we swap x and y. So y is the root of x plus 3. Notice the plus 3 is outside the root. So if I'm doing this properly, I should have a little hook on my root just to indicate that, hey, this 3 is outside this root. Been sloppy all around here. There. And then I can write y as f inverse of x. So the inverse of x is the root of x plus 3. We found the inverse on the restricted domain, but I think you know what's coming next. We're going to check our work using function compositions, right? So now, confirm, I'll call it part B. There was no part A, I guess, but confirm f inverse of x is the root of x plus 3 is the inverse of f of x equal to x minus 3 squared on the restricted domain. Using function compositions. We've done it once already. So I'm just going to jump in and start, right? And I'm gonna do both just for more practice. I'm gonna do f of the inverse of x, does it equal x? And on this side, I'm gonna do the opposite, f inverse, oops, of f of x, does it equal x? I'll put a little divider there. So we have f of x, we have the inverse. So here we go. F of x is x minus 3 squared. And wherever I see an x, I'm going to use the inverse root x plus 3. Treat it as one thing. So I have the root of x plus 3 minus 3 squared. That's going to be the root of x plus 3 minus 3, and then leave the square on the outside for a little bit. And so now I have the root x squared. But the root x squared is just x. Right? Because plus 3 and minus 3 are going to cancel. I didn't write that, but should have. So usually these compositions are not terribly elaborate, right? It's more of a mind game to try to stuff inverse into the original function and vice versa, right? But then once you have them in there, then it should fall out relatively quickly. Okay, what if we stuff the original function into the inverse? So now I have the root of x minus 3 squared plus 3. The root of x minus 3 squared, well, the root is going to cancel with the square, and so I'm left with x minus 3 plus 3, which usually equals x. Therefore, the inverse we found is in fact the inverse on the restricted domain. I'll say, since f of f inverse of x equals x, which is the same as the inverse of f of x, we have found the inverse. I'll add on the restricted domain. You could do the same thing for negative infinity to 3 if you wanted. What would change? The only thing that would change is here, right? We cut the negative, but then you would only get negative values and you'd cut the positive option, but it would end up being the same. But like I said, I like to work with the positives just because they're nicer. So what does the inverse look like if we graph it? So now we know that the root of x plus 3 is the inverse on this restricted domain. Okay. So let's see, what does that look like? The root of x, and then step it out plus 3, so you don't have the plus 3 under the root. Okay, that's kind of hard to look at, I think. What if can I do something weird here? Can I restrict? Oh, I want to show it. I feel like I can restrict the domain on here, but I can't remember how, so that's okay. What I'm going to do is I'm also going to draw y equals x, so a diagonal line on where y equals x, or x equals y, right? And there's a method to my madness here. I'll take a screenshot. Because as a rule, the inverse of the graph, hey, is going to be a reflection around that diagonal line. That's kind of cool. So here, try to use the same colors. This is y equals x, and we were looking at this blue, and then we found this green is the inverse, right? So if you ignore everything else, then if this is the original, then if I reflect it around that diagonal line, the y equals x line, then I'm at the inverse. That's really difficult. I find that that's really difficult for me to kind of imagine the flip around the diagonal line, but it is a fact. It's how inverses work. And so notice, it is a nice way to be able to check your work though. If you have Desmos going on the side, then you can check that your inverse and just convince yourself that it is a reflection around the y equals x line. So notice the inverse is a reflection over y equals x, which is a diagonal or the diagonal line. So it's just a property of the inverse, graphing property. I don't like to make you graph things by hand too much, right? Beyond kind of visualizing and being able to restrict the domain like we did with this question here. Right? But I'm not going to get you to draw the inverse of some weird function because that's hard. Okay. Good. Any questions about that? Let me just confirm. I think that's the end of my, yeah, it is. The end of inverses.
Pretty much just another transformation.
Yeah. Just flip it.
Transformation format.
More math. A lot more math, I think. Yeah, did it satisfy your need for inverses?
Definitely not.
More math. There you go. Okay. Let's see here. That is the end of chapter 1, if you can believe that. Maybe I'll write that in our notes. Whoops. I'll do a review of 1 and 2 later. The end of chapter 1. Whee! So chapter 1 introduces a lot of concepts, mostly about functions and things that we need to have a handle on. And what gets kind of weird in chapter 2 is now we're going to go back to linear functions, just straight lines, y equals mx plus b type of stuff. And we're going to talk about just properties of lines. And so, but now we know a lot more about functions in general. Okay? And so it does feel a little bit weird to now go back to lines, which we've already talked about briefly. But linear functions are important. And so here we go. Linear functions, they're just straight lines. Right? You might remember y equals mx, oops, helps if I write the m, mx plus b from high school, right? Is any equation of a straight line. Right? This projector is not happy today. The general setup of a line how do we know if it's a linear function? If I just have a y and an x, and I can rearrange and just get one term of x, right? No x squareds, no x to the 3s or anything like that, no polynomials yet. We'll get there. But for now, just one value of x and one coefficient of x, oops, one coefficient of x and one term on its own potentially, right? Then I have a straight line. Okay. If you're running a coffee stand, the labor cost is $90 per day, and the per cup cost is $1.30. So we want to find the cost, let's see here. I had to think about it for a little bit. So the cost is going to increase with each cup. So if I want to write a function that summarizes the cost, right, what do I have to take into account? So here, should I use D for dollars instead of a capital C and a lowercase c? Maybe. D for dollars. Right, could use C, but what would that look like? So now, or capital C of C, which we do often, but because it's our first example here, let's, and I'll write here, because capital C would be confusing. Or could be confusing. If you like it, go for it. So now, my function is going to take some input, the number of cups, right? And it's going to return the dollars at that cup level. So it costs me $90 even at 0 cups. Someone still has to work the stand, right? And so there's that basic just $90 per day that it will cost. And then it's going to be $1.30 per cup. In a graph, so it's the dollar, it's the cost that we're talking about. So yeah, your revenue would be negative, but when we're talking about the cost to us, we can ignore that. But yeah, good thinking. But by talking about the cost to us, we don't have to worry about that. So then the output is going to be the dollar cost, the dollars, and this is the number of cups is the input. Even at 0 cups, right? I'm going to start at 90, which we might remember still from y equals mx plus b, right? Whatever is attached to the x or the c in this case, whatever is attached to the variable is the slope. And whatever's on its own is the y-intercept, which we usually just call the intercept. So if we want to graph this, then the cost, let's put 90 here, would look like this. So it'd start at 90 at c equals 0. And then for each additional cup, it increases by $1.30. So you could do 1 cup, but how about we do 10 cups because it gives us a nicer number, right? At 10 cups, I go up, what, $13? c equals 10, let's say, puts us here at 90 plus 13, so 103. And it's linear, so it keeps going and going and going and going. Now, can I try to connect these dots? A fun thing about linear functions is in order to draw a straight line, you only need 2 dots because all the other dots are going to be on the same line. So as long as you have 2 dots, then you can connect them and extend the line. And usually, you know, you're working on paper, so then you can just use, I like to just bend my page and use that as a straight edge. Or if you have a ruler, cool, but usually I don't. I just kind of use the edge of my paper as a straight edge. It's harder on here though, because it kind of like springs into I think I do actually. Let's see here. Boy, okay. I do, but can I use it? Be all cool. Can I draw along it?
Yeah, draw along it.
Wow. Something new every day. It's almost beautiful. Because I didn't quite catch the bottom. But cool, thanks. That's nice. So now this is the dollar cost for all the cups, right? So now we have this linear function. And so one thing to note, in order to draw a straight line, which is a linear function, we only need 2 points. Connect them and extend the line. That's kind of cool. We've already talked about a lot of these, but it doesn't hurt to see it again. So a linear function, right, we can always have just y equals mx plus b or b plus mx, like we saw 90 plus 1.3 times c, right? And so it doesn't matter, even if you have kind of a0 plus a1x, right? As long as there's just one x in there, then it's a straight line and you can rearrange it. So b is the initial or the starting value when the input is x equals 0, right? Which we saw, okay, even if I sell 0 cups, it's still going to cost 90, right? It's my starting point. M is the constant rate of change of the function. We usually call that the slope, right? So here, this is the slope. But notice, we've already talked about the rate of change, right? Find the average rate of change of this function, right? And so, and it's going to come back up. And so we've already seen the rate of change and worked with the rate of change, but it is the slope. Okay. So just as a note, in this textbook, he's thought of everything. He uses b plus mx, even though we usually say mx plus b, but then when we talk about it, we talk about it as, okay, the output starts at b and then increases at a rate of m. And so that's why he uses b plus mx. I just thought it was a cute thing. That's why in the examples he uses this format, but they're correct either way. So the slope is going to be very important, right? It's the only thing that's kind of doing anything in our line. Otherwise, we just have a straight line with a slope of 0, right? And so m is the constant rate of change of the function. And we can also talk about if the function is increasing or decreasing, right? Going back to the average rate of change, if you found a positive average rate of change, we said it was an increasing function, okay? And if you found a negative rate of change or average rate of change, you said it was a decreasing function. So we can just draw these scenarios here. X and Y. If it's increasing, let's see here, I'll put it. Slope is greater than 0, right? So it's positive. If it's decreasing, looks like this. M is less than 0, right? So if you have a negative slope, then it's going to be decreasing and going down like this. And then the last one, oops, is a slope of 0. If the rate of change is 0, then the output is just going to be b all the time, right? Which is just the horizontal line. So it doesn't matter what value of x you put in here, you're always just going to be at b, right? The intercept. That should be a b here. So a horizontal line has a slope of 0. Okay. Good. The value of a car depreciates over time according to this equation. And so we're going to be able to input time, t, and produce the value after that amount of time. And so here, I want to say that t is denoted by lowercase t almost always. And value at some time point is going to be v of t. Okay. We're just asked to interpret the equation, right? And so the value at any time point t is going to be 13,000 minus 2,000 times t. Let's clarify that t is probably in years. I hope. Why do I hope? What if it's per day? Think about it per day. Uh-oh. This is the initial value of the car, right? This is what you bought it for, 13,000. And then the value is going to be decreasing by $2,000 per day. No, per year, right? If t is in years, right? So that's why I said hopefully t is in years and not day or anything like that. And so our interpretation is, well, how deep do we want to go? The initial value of the car is 13,000. And then the slope is negative 2,000. Which means that for each additional t, right, the value is going to decrease by 2,000. So for each additional t, the value will decrease by $2,000. It's negative 2,000, but when I said decrease, that takes into account the negative. And so I think this is a nice point to introduce just the general definition of the slope and the intercept, because if you have the general definitions, or the general interpretations, I should call them, then you can apply them to any scenario. Okay. And so do I have enough room here? No, I don't. Probably didn't mean to introduce it here, but I'll just do it here. The general interpretation of slope and intercept the slope. Let's say m, right, in y equals mx plus b. So the slope, the general interpretation is that for each unit increase in x, right, or the input, for each unit increase in x, we will see an m unit increase in y. Now I say increase, right? A negative $2,000 increase is a decrease, right? So if you want to, as you're starting, then you don't have to worry about making those conversions, because you don't want to say that it's a negative $2,000 decrease, because a negative decrease is an increase, right? So you don't want to trip yourself up. So I would, pardon? You can say, well, yeah, you could say change. But usually we talk about increase or decrease. But I would just use, for when you're first starting, just use a negative 2,000 unit increase in the value, right? And then eventually you're going to kind of say, well, that's probably a $2,000 decrease. But technically this is correct. The key here is for each unit increase in x, right? So for each additional year in the previous example, right, the value is going to decrease. Uh-oh, I need to do the intercept. B. This is the value of y when x is 0. And it's that x equal to 0 that we're going to hang our hat on. With my last moment on this page, this looks familiar, right? We've already seen this. It's the average rate of change. Recall the average rate of change. And when we talked about the average rate of change, I brought up the slope as rise over run, because it is an average rate of change and it's the one that we're most comfortable with, right? And so we can also use the function notation f of x2 minus f of x1 over x2 minus x1 to find the slope. Okay. We'll stop there. And I'll post the assignment, but I'll bump the due date a little bit. I think I can't remember when I set it for, but because we didn't get very far, but I think you can do a lot of it already. All right, if you have any questions, let me know. Otherwise, have a wonderful long weekend. I'll see you on Tuesday.